Okay, it's just turned 4 o'clock, so we'll get going. I've been doing a workshop earlier this week. I've already presented 700 slides of code this week. I reckon we have time for another 80 or so now. So, my name is Rob Smallshire. I work for and part own a consultancy based here in Norway. We work in various domains, but mostly they have a science and or engineering flavor to them. I've been working with C++ since about 1995 or 1996. I discovered Python in either 2000 or 2001. So I've been working with both these languages for quite a substantial period of time. It's fair to say that my use of C++ has tailed off in the last 5 or 6 years, simply because of the kind of projects I've been involved in, and to use an unfortunate metaphor, my C++ has become a bit rusty. So some of the C++ you see here might remind you a bit more of C++ 98 rather than C++ 17. So I'm going to talk about integrating Python and C++ together with a library called pybind11. So why might you want to do this? Well, one of the key motivations for doing this, and the one that's going to motivate the example in this talk, is that you already have a useful, valuable, debugged piece of technology in one of these languages, and you need to use it from the other one. So in the example I'm going to give in the talk, we have a very high quality C++ library that's been around for a very long time, and I would like to use it for whatever reason from Python. So although I don't really believe you should ever design with reuse in mind, if you have something very useful, it makes much more sense to reuse what you already have rather than trying to rewrite it from scratch in another language just because it's another language. And C++ and Python are interesting complements. They're opposite in almost every way, but in spite of the fact that they live at opposite ends of various spectrums, they do complement each other very well, and they can be made to work together very elegantly. So C++ is very fast. Arguably, it's as fast as we can go without dropping down to assembler. Python is very slow. Even compared to things like JavaScript, it's very slow. You're looking at Python being nominally 10 times slower than C++, perhaps even 100 times slower. So you don't go to Python for performance. On the other hand, as I experienced while I was writing the code for this talk, you don't go to C++ for productivity either. It can take a long time to write the code correctly. It can take a long time, you spend a lot of time just waiting, is my experience, for the compiler and the linker. So in terms of productivity, I find that I'm much more productive in other languages which don't have that compile link cycle. I can just run code immediately. There are a whole bunch of libraries out there for helping you adapt C or C++ code to Python. There's one called Swig. Even the author of Swig recommends that you don't use Swig. I met with him at EuroPython in Edinburgh a few weeks ago, and over a few beers he confessed that he wished he'd never written it. So don't use Swig. There's a thing called C-types, which is built into the Python standard library that allows you to call C functions, but not C++ functions. There's a thing called CFFI, the C foreign function interface, which is kind of clever because you can essentially import a C header file, the text header, into CFFI and then call the functions within it. That's quite nice. There's Boost Python, which is, as its name suggests, part of the Boost library. That's still very much, it is compatible with C++ 98 and 11, etc. But it's also weighed down by that compatibility, and it's become extraordinarily complicated, and nobody wants to maintain it. The guy who wrote it is now the lead developer on Swift for Apple. So we're left with pybind11, which is much newer, has ditched a lot of the legacy stuff that was really awkward to do in C++ 98, embraced C++ 11 and later. Coincidentally, this adapter is from the Norwegian Wikipedia page on adapters, and it looks incredibly dangerous to me. How do I isolate the other hot pins when you plug it into one of them? I don't know. There are on that thought, let's move on. There are two basic architectures, if you like, of when it comes to how we can use Python and C++ together. We can extend Python with C++. This basically means we can write Python modules in C++. It's important to realize that Python is itself written in C. And in fact, when you run the Python executable is a very small executable, and all it really does is load the Python library, libpython, and pass it some arguments, and create an interpreter. So once you realize that libpython is a C library, it becomes a bit easier to understand how these different languages can talk together. We can write modules in C or C++. libpython will load them. These modules will use the Python C API. Python has a C API for its interpreter and all of its built-in types. And our C++ modules can also use existing libraries, which might be third-party libraries, as they will be in my example, or they might be existing libraries in your own domain that you have made. The other approach, which is a bit trickier to make it work, but is very powerful, is embedding. So you already have some existing application in C++, say, which is using some libraries, and you can have your library link against and use libpython, and it can instantiate a Python interpreter running in the same process as the rest of your C++ application. It can then load your modules written in C++, and your modules in C++ can call other libraries in your application, or indeed the original library in your application, all within the same process. So at this point, you've embedded a Python interpreter into a single program, and you essentially have a single application running in a single process where you can choose which parts of it you now write in C or C++. So that's a typical approach for adding a scripting facility to an existing application. So for the purposes of my talk, I need an example. I need a library to wrap, preferably open source, preferably C++, preferably not entirely straightforward C++, to make it a bit more interesting. So I've chosen to wrap a library some people here might be familiar with, called Seagull. Seagull is huge. It's the computational geometry algorithms library. It's a good candidate for wrapping. It's very fast. It's in C++. It's very robust. Anyone who's done any computational geometry will know that writing robust geometric algorithms is incredibly hard. It's got some very sophisticated mathematics in it, so it knows when floating point numbers aren't sufficient and will switch to multiple precision numbers internally so as not to lose precision. So clearly, rewriting something like this, or even a small part of this in Python so that I can use it from Python, is a non-starter. Seagull has been developed over maybe 20 years or more, so it's a major, major undertaking. I'm going to wrap a very tiny part of Seagull that deals with a thing called constrained and conforming triangulations. These are great to use from C++. I'd like to be able to use them from Python. So let's go. So I'm going to start by showing you a C++ program, which is using Seagull. It's an application, if you like. And we'll talk you through what that program's doing. And then when I've shown you the C++ program, we're going to set off and try to make that same program in Python. So typical C++, we have to include a big pile of includes. We go off and define a bunch of types. You can see that these aren't entirely straightforward types. We've nested templates many, many levels deep here. The key thing is we're creating things like triangulation data structures and defining points and vertex handles, all the things we need to interact with a triangulation. Here's my main program. The very first thing I do is I create a CDT. That's my type def for a constrained Delaunay triangulation in 2 dimensions. In the next part of my program, I'm going to have an unrolled loop. I wouldn't normally write code like this, but I've unrolled it for clarity. So here's the unrolled loop. I'm going to insert a bunch of points into the constrained triangulation. And each time I insert a point, it returns a vertex handle, which is just an opaque handle onto the point I've just inserted. Here are my points. Next, I'm going to insert some constraints. And a constraint is just a pair of points that I've already inserted, which define an edge in the triangulation. And they set up a rule in the triangulation that no triangles are allowed to cross one of these red edges here. So these are constraint edges. And while I'm doing this, behind the scenes, Seagull is actually maintaining this triangulation data structure. Now I'm going to create a thing called a mesher. You'll notice that the mesher wraps around the constrained triangulation. And the mesher allows me to specify seeds. So I've created a vector with 2 seeds in it here. And I pass the iterators to that vector to set seeds on the mesher. You can see the 2 seed points in yellow here and here. And the seeds allow me to control which triangles in the triangulation I'm actually interested in, or not interested in this case. We can strip away the parts of the triangulation that are of no interest, in my picture at least. Now I'm going to ask Seagull to make this triangulation conform to some geometrical rules, to conform to a thing called the Delaunay property. It doesn't matter what it is, but you'll see when I do that, where it says watch here, the triangulation changes and we get some new triangles. I'm now going to make it conform to the Gabriel property, and we get a few more triangles. Then I'm going to set some meshing criteria and ask Seagull to refine the mesh. I'm going to set some properties that control the minimum angles on the triangles. Small angle triangles aren't very good when you're using them in simulations. And set the triangle size. Now we get a nice triangular mesh. And then I'm going to ask Seagull to optimize that mesh, doing a thing called Lloyd optimization, which makes the triangles more even. There we go. So there we are, beautiful mesh. So the problem is, from my point of view, is I'm interested in triangles, and even trivial changes to this program take me quite a long time. It's at least 30 seconds if I just hit compile and run. Right? The Seagull is not a straightforward library. It's extremely generic. So it takes a long time. Seagull also uses boost. So it's pretty slow around this circuit. So what can we do? Well, we can try to wrap it using pybind11. So this is a structure. I think this is one of the hardest things when you're starting something like this, is how do you organize stuff? Where do things go? In a sense, writing the code is the easy bit. Getting to this point of understanding where to put things usually trips me up. So I'm going to have an example program, triangulate.py. I've got pybind11 in a lib directory. I need that. I'm going to be using it. I've got the library I'm wrapping, Seagull. That's going to live in here, specifically this header here. And then I've got my source directory, which is where my wrapper is going to live. Inside source, I have Mesher. Mesher is a Python package. It's just a directory on the file system that has a thing called, this is pronounced dunderinit, has a thing called dunderinit.py in that directory. And it has seagullmesher.cpp, which we're going to write. And I can optionally have some C++ tests and some Python tests. I need to build the C++ with CMake, and I need to explain how that build works to Python with a standard setup.py. So let's just start off writing some Python. So I'd like to do something like this. Import mesher Seagull mesher. This is my outer Python module. This is my inner Python module, which will be written in C++. And of course, I can't do this yet. It doesn't exist. So we need to begin writing some code in here, in seagullmesher.cpp. So this is just about the simplest pybind11 module. We include pybind11, set up the namespace alias, and then use this macro to set up the module name. And M is a C++ object that represents the concept of the Python module that we're making. We now need to build it. So we need a CMake lists. I'm no fan at all of CMake. It's emerged as something of a de facto standard, so I'm going to try to use it. And we have a CMake file which says the project is Seagull Emeasure. We're using Seagull. Seagull uses Boost, so we need that as well. And we're telling it about pybind11. Pybind11 comes with CMake support, which is why I'm using CMake. And then all I need to do is use this Seagull function here, pybind11 add module. Here's the module name. Here's where to find the source code for the module. And CMake will do its thing. All Python modules that are packaged up need a thing called setup.py, which uses setup tools to package up Python into something we can redistribute. So I need a setup.py as well. Setup.py files are usually pretty simple. They usually look something like this. Just, the name of the module, the version, who wrote it. We need to explain in setup.py that this code needs to be compiled using a thing called CMake extension. Unfortunately, we have to write CMake extension, which looks like this. It's just horrible. Fortunately, this is just boilerplate, and you can copy and paste it, and you can copy and paste the other half of it as well. There's quite a lot of code in here required to make setup tools talk to CMake, but you only have to write it once. In fact, you can just do what I do and just cargo cult it and copy it off the internet. So, now we need to run setup.py, and when you give it develop, that argument there is usually things like develop or install. Develop means that I want to be able to install the code in such a way that I can still develop on it while it's installed into my current Python. So we run this, it goes away, setup.py equals CMake. CMake does the compiling and linking. We're done here. It's built. That takes about a minute. Let's start at Python. Here we are, Python 3.7. Import Emeasure, Seagull Emeasure. Great, it works. We've got imported the C++ module. We can ask for help on the module. It's not very interesting. There are no classes nor functions in here yet, but you can see that the module is implemented as a shared library here on my Mac. Normally, when your module is written in Python, you get the path to a .py file here. So the module is just a dynamically loaded library. So now let's crack on and start building the mesh from Python. So in my little test there, I just did import Emeasure.Seagull Emeasure. I'm going to switch this around. So it's from Emeasure Seagull Emeasure import constrained Delaunay triangulation as CDT. In Python, we can rename things on import, which is very handy. So here's my very basic Python program. Those of you who aren't familiar with this, this is how you tell Python what to do when a module is executed. And what it says is, when this module is executed, call main. In main, we instantiate a CDT and call it CDT. Simple. Okay. Our module's not very interesting yet. So to get that to work, we need to tell, in C++, we need to use pybind11 to explain that we want to wrap an existing type, CDT, and we want to call it this in Python, and it must have a default constructor. Okay? Notice the underscore here. This is not the class keyword. This is a function within the pybind11 namespace. But I hope you agree that's fairly readable. You'll see why I have this slightly odd placement of semicolons in a moment. So we need all the includes and all of the. I've got fancy here with my C++. This is I've moved away from type defs, you see, to whatever these are called. And now I'm using. So I need all of this just to find out what CDT is. Okay, so I can use it here. Okay. So next, what do we need to do? We need to insert the points into the triangulation. So I'm just going to take the same unrolled loop approach that I took in the C++. So in order to get this to work, what do we need to implement? Well, we need to be able to import point so that we can get hold of that. We need to wrap the point class. We need to wrap the insert method on the triangulation. And we need to, even though this vertex handle type is never named in Python, because Python is dynamically typed, we need to have wrapped it so that this function is able to return it. Because insert returns this vertex handle. So back to the C++. We're not quite doing TDD here, but we're definitely driving the implementation of this module by requirements in the client code. So inside the module, we need some more code now. We need the point class, so I have to define the point. CDT gives us a type for that. And this is pretty much the minimum useful point. Again, Py class. I'm wrapping the point. In this module, I want to call the point this in Python. I want to call it point. And I'm going to define an initializer for it that takes 2 integers. And I can tell pybind11 what I want the arguments to be named in Python. Python allows named arguments, and we can explain that to pybind11 by using this pyarg. That's pretty minimal. I'm going to go a bit further. I'd also like to be able to construct my point from 2 doubles. This is kind of interesting because we don't have overloading in Python because it's dynamically typed. But when I'm writing a Python module in C++, I can overload functions. And the machinery is smart enough to dispatch to the right one depending on which one I'm using, on the actual dynamic type at runtime. So there's quite a lot of machinery in pybind11 to make all of this work. I also want to add a couple of properties. So in Python, we have properties, which enable us to access the attributes of objects without going through a function call. Okay? We don't need the parentheses on the end. I'd like these properties to be read-only. So I use def property read-only. I'd like my properties to be called x and y. What do? They call these 2 functions. So here I'm passing a pointer to a member function here. Okay? So whenever I get that property from Python, it will call that C++ function. So this is quite nice. And it's quite readable. And now you can see why my semicolon is here, because all of this is one statement, and these are chained method calls. Make sense? Now, whenever I'm teaching my Python classes, I strongly encourage people to implement a special Python method called dunderrepr _repr_. And dunderrepr is the special Python method that gets used to display objects to the console, particularly in an interactive session. And it's much easier to debug your Python programs if the objects know how to display themselves. So we are going to define dunderrepr here. And my dunderrepr implementation is going to be a lambda. And I'm going to use some fairly horrible string concatenation here to put the description of that object together. So I'll start with the string point, and I'm just going to convert the coordinates to strings and make it look nice. So it's very important to remember dunderrepr if you want to have a nice development experience when you're working from Python, especially for a value type like point here.
Got a question?
Yeah?
I thought that dunderrepr was that Python interpreter was supposed to be able to bootstrap on dunderrepr, whereas dunderstring or str was more like what you mentioned now. Yeah.
I do have a comment on that. Any object you have in Python will inherit dunderrepr and dunderstr from the object base class. Dunderrepr is really intended for developers, and dunderstr is intended for the rest of the human race. So that's generally how you organize things. So put that way, I would say you should always have a dunderrepr, because otherwise you're going to get the inherited dunderrepr from object, which just prints the object address, which is not very useful. Yeah?
Maybe later explain how to deal with different Python classes like Numpy and so on. Is it possible to convert back and forth
I'm not going to cover that today, but there is support in pybind11 specifically for Numpy and some other very popular numerical libraries. Yeah, so you can do things like access Numpy arrays from C++. Yeah, I'm not going to show that today though. So we also need to wrap this vertex handle. Vertex handle, we don't need to say anything about it. All we need to do is be able to own a vertex handle from Python. It can be completely opaque. So this is very concise. We just have vertex handle in this module called vertex handle. Okay, and then we need to add the insert method to our triangulation class. So the insert method here is again bound to this lambda, which just calls cdt insert. Why have I used the lambda rather than a function pointer like I did before? It's because insert is overloaded about 37 times. And you have to get into quite unpleasant syntax casting the function pointer to explain exactly to pybind11 which overload you want to call. Using the lambda avoids that, and frankly, it's just easier to read. Okay, so that's inserting the points. Now we need to insert the constraints. These accept vertex handles, these opaque objects. So let's see how to do that. Actually, let's see that we can't do it yet because we have no insert constraint. We run our Python program. So insert constraint is going to look like this. Again, it's going to be bound to a lambda that accepts two vertex handles and just calls insert constraint. So you can see most of these wrappers are really straightforward, extremely simple. And you have quite, I haven't done it yet, but you have a bit of freedom. You can call the method in Python something different to what it was called in C++. You'll see that come up soon. For my own convenience, and so that I can debug the thing and make sure this is actually working, I'm just going to add a couple of functions which get the number of vertices in the triangulation and the number of triangles in the triangulation, faces. These are implemented using function pointers. Okay. Let's crack on. So now I run my program and I've inserted 28 vertices. Moving forward. Next thing I need to do is insert these two seed points to explain which parts of the triangulation I'm interested in. And this is a little bit more interesting from a wrapping point of view. In Python, I'd like to be able to write this. I'd like to be able to create my measure, create a Python list with two of my points in. Remember, these are C++ objects. This is a Python list containing two C++ objects, and I'd like to pass my seeds to measure.seedsFrom to tell the measure about these two seed points. I'd like my seedsFrom to be very generic from a Python point of view, so that seeds can be any Python iterable. Not just a list, as it is concretely here, but a list, a tuple, a set, just any collection of points. So I'd like this to be quite generic. I struggled a little bit with this, reading I have to warn you, the pybind11 documentation is not fantastic. It's pretty bare bones. So you have to spend a bit of time working things out for yourself. Pybind11 gives us an iterator type, which is a wrapper around Python iterators in C++. It gives us pyiter, which can take an iterable object and give us a Python iterator. And what I can actually do with pyiterator is a C++ iterator wrapper around a Python iterator, right? So it looks like an STL iterator, but its implementation is a Python iterator as implemented by the Python virtual machine, by the Python runtime. So setSeeds is just expecting any forward iterator, which has a value type of points. So I can give it my Python iterator here. This actually fails, and it fails because the iterator doesn't know that its value type needs to be point. Its value type is just pyObject, which is just the most generic thing. So that doesn't really work. To make this work, to adapt my Python iterators to my C++ iterators, I had to write an iterator class, an iterator template class called typed input iterator. And you can see here that I'm taking my Python iterator, adapting it to my typed input iterator with a value type of point, and then passing those iterators to setSeeds in Seagull. Yeah? The only interesting thing that typed input iterator does is call this cast function from pybind11, just to make the type conversion work. All the rest is just iterator boilerplate. But it works. Okay, now I need to wrap my conforming Delaunay and conforming Gabriel functions. This is very straightforward. The module object has a def. I can give a function name, a function pointer, an argument name. I should have done this throughout. I haven't for space reasons, but you can also give a doc string, and that will be accessible from Python. So when you do help in Python on your module, you can get the documentation that you've written on the C++ side of things. So that's quite nice. Okay, so let's run our program again. We're doing quite well here. So we start off with 28 vertices, we do the Delaunay conforming and we get 31, we do Gabriel, we get 37. So the program seems to be working. That's good. Now I need to refine the mesh. And for this, I need to wrap this criteria object, or create this criteria object, which is a seagull thing again, which the mesher uses to decide how to do the meshing. So back in C++, we have to write all of this. We have to create the criteria object. Notice now, new thing here, pyarg doesn't just allow me to name the argument, it allows me to specify a default for the Python function from C++. So I can do default arguments here too, which is nice. And then on my mesher here, I've just added, I've added def property. So before I had a property read only, this is a read write property where I can set the criteria. The property setter is this function pointer. The property getter is this function pointer. The property setter is this lambda, which just falls through to set criteria. Again, I use the lambda there to avoid casting function pointers. Okay, how are we doing? Let's run our program again. Obviously, rather than me just running the program all the time, I should have some tests, but then that would be even more code for you to look at. So after the mesh has done its work, we've now got 431 vertices. So everything seems to be working nicely. And then the last thing we need to do is this mesh optimization step with Lloyd optimize. This is pretty straightforward. Actually, no, it's not straightforward. And it's not straightforward because Lloyd optimize uses some quite clever machinery from Boost to allow you to do named arguments in C++, which I won't even pretend to understand, but in order to wrap it, I had to write all of this in order to be able to call Lloyd optimize mesh 2. But again, you can see my use of pyarg here to specify the argument names and the defaults. So at this point, I think I've got to the end of my original C++ program and reproduced it in Python, which is nice. And of course, fiddling with this Python program and running it again takes literally 2 seconds, whereas fiddling with a C++ program and running it again took me at least half a minute, maybe longer. Right, now I need to, this program is great, it allows me to build a mesh, but I can't actually access the mesh. I can't iterate over it or get hold of the triangles or do anything with them. So how do we do that? How do we get the mesh out? Well, Seagull defines on its triangulation some iterator ranges. Vertices begin to end and faces begin to end. This finite is here because triangulations have vertices at infinity for reasons I'm not going to begin to go into. And so what I'm doing here is I'm saying I want finite vertices function on my constrained triangulation object. I want it to return a Python iterator, and it's really straightforward to use. It looks like it is. I just call make iterator, give it my C++ iterators, and it returns a Python iterator that wraps them. That's really straightforward. Same for the faces. When I was writing this, I ran into real trouble figuring out what the value type of these iterators was, because the Seagull templates are nested so deep, and I was tracing this through the code, trying to find out what the value type actually was, because I needed to expose that value type to Python so that the iterator could be dereferenced. Fortunately, the solution came in the elevator this morning, which I was sharing with some world-renowned C++ experts. He gave me the key piece of advice I needed. And the key piece of advice is that you need to go to Stack Overflow and paste in this type name function, which allows you at runtime to print out as text the actual type of a thing you have in C++. So I actually wrapped a function called print faces iterator value type, which calls type name on finite faces iterator value type, because I had no idea what this type was. And then I was able to print it out. And when I printed it out, I wasn't much wiser. So I pasted it into my text editor and reformatted it and got this. So that was the actual value type of the iterator, which I was struggling to find. So the reason Seagull is like this is because you can parameterize it on things like the type of float, right? You can put your own number types into it. So it's extremely generic. But I did struggle with that, I admit. I got a great hint this morning in the lift. Yeah. So anyway, the iterators work once you figure out which types you need to expose. Another important thing I've added, which you'll see why in a moment, is point is a value type. You know, we don't really deal with points by reference. We copy them around. Okay? And it's very important that for value types, especially if you want to use them in like a dictionary or a set in Python, that they know how to generate a hash code and that equality is defined for these things. So I've had to define dunder hash, which makes a type in Python hashable, and dunder eq, so Python understands how to compare things for equality with the double equals. So you can see they're fairly straightforward. Dunder eq just falls through to the equality operator in C++. Dunder hash is a little bit more involved. I was very happy to see that C++ now has std hash. So I was able to use that to generate my integer hash code based upon the hashes of the x and y coordinates. So that seems to work. So now a slightly more interesting Python program using all that stuff. So this is a complete Python program. We take in some command line arguments. I get the file name for an edge file that's going to contain some edges, just some line segments. I'm going to take in a file name from mesh file name, which is what this program is going to write out, and I'm going to take in a number, which is the size of the mesh that I'd like to produce. I'm going to create a constrained Delaunay triangulation. This is my Seagull object, created from Python. I'm going to open my edge file. For each line in the file, I'm going to read the line. I'm going to split it up at white space. I'm going to map each field through the float function to turn it into a floating point number, and I'm going to unpack the result into ax, ay, bx, by. So they are 2 points at the ends of a line segment. Okay? I use these to create the 2 points a and b, which I insert into my triangulation, and then I insert the constraint edge between a and b. So these are those 2 vertex handles that came back. I just pass them straight back to Seagull here. I never need to know what they are. They're just completely opaque types. Then I refine my triangulation by making it Delaunay compliant and Gabriel compliant. I create my mesher, do some meshing, do the Lloyd optimization on the mesh. And at this point, I've built a nice mesh, but it's living inside the C++ data structure. So we need to pull it back now so that we can access it from Python. So what do I do here? I build a dictionary which maps points, which are now hashable, so they can be used as dictionary keys, to an index of the point. So the first point is index 0, the second point is index 1. I use enumerate to generate those indexes. This is the dictionary key, the vertex point. This is the value, the integer. So for any point, I can say, which index are you at? So I'm just building that map in Python, that dictionary in Python. Then I go through every triangular face, for face in finite faces here, and I ask that face for its vertex handle at indexes 0, 1, and 2. So they are the 3 corners of every triangle. Okay. And then for the 3 corners of every triangle, I look up in my dictionary I built up here what the index is. So anyone who's ever done any graphics might know about like V-lists and T-lists for triangles. So we have a list of vertices and we have a list of triangles, and each triangle is represented as 3 indexes into the vertex list. Quite a simple thing. And then we, at the end here, we just write out into the mesh file the number of vertices, print out each vertex, the number of faces, and print out each triangle. So the input file to this program looks like this, 4 numbers per line, so that's x, y, x, y for points. We read those in from coast.edges. We run our program, Python make-mesh.py coast edges to coast mesh with a size of 0.125 for the triangles. It writes out a file that has 89,000 points in it and 178,000 triangles in it. The whole process takes about a second, including all the file I/O and the triangulation and everything. There's no way I could do that in Python. If I wrote that triangulator in Python, it would take 10 minutes. And we get a nice mesh. And we're done with 3 minutes for questions. Thank you. You can just stare at that because it's beautiful. Any questions?
So I take it you recommend pybind11 in general?
I think if you're going to do, I'm going to just put my microphone back on. So the question is, do I recommend pybind11? I think if you're wrapping C++ today, pybind11 is the way to go. If you're wrapping C today, then C types or CFFI might be sufficient and is probably quite possibly less work. I mean, if I just had something where I wanted to call like 2 C functions, I'd just use C types, because then you don't need the whole kind of build system stuff to go along with this, and which is where a lot of the complexity is. If I was doing C++, I'd definitely go for pybind11. I cannot imagine a case in which I would now use Boost Python. I think pybind11 has superseded it, and thankfully pybind11 APIs are very close to the Boost Python APIs. So migrating is not free, but it's straightforward. What questions do you have? Yes. How long did it take to do? Sunday and this morning. Plus a bit of time on the slides. Yes?
You have to manually specify every function and type that you want exposed to Python.
Yeah, there's no magical just wrap this class.
It sounds like there should be.
Yeah, it does feel like there should be. Yeah, I'm not sure why that is. I mean, it's quite often C++ classes have a lot of stuff in them that you don't want to wrap. You know, and I can, you know, for example, I mean, you have like vertex begin and vertex end. I don't want to wrap those to Python, right? I want it to appear as a Python iterator, which is just give me a vertex iterator. So what is 2 functions in C++ really has to become 1 function in Python to be Pythonic.
Yeah, but would you specify the Pythonic API in pybind, in the C++ bind encode, or would you rather have that more C++ and just specify it, I don't know, a Pythonic API wrapped around that? It sounds harder to write a Pythonic pybind thing than writing a C++ thing.
Yeah, I don't think it's hard. I mean, there's a few patterns you need to figure out, particularly with adapting iterators. But beyond that, just regular functions are really straightforward to wrap, I think. So it's not a lot of work. You know, I'd be quite comfortable just, well, I have done, you know, just sitting down and making one of these wrappers quite quickly. Where the time goes is in getting the thing to build for the first time, right? That is, well, on every project I've ever worked on, I think that's been true. So, but particularly so in this case, because there's a lot of moving parts, and you have to worry a lot about binary compatibility between your library that you're wrapping and the Python interpreter, and possibly the application you're embedding it into. So you spend a lot of time worrying about those kind of things. Yes?
Yeah, but just to follow up on Paul's question now related, the way I interpret your binding or wrapping is that you have written no Python code.
Correct. I did have an outer Python module, which I didn't use.
That had no code.
It had no code in it, right? You can put code in there, and then, of course, then you have the opportunity to write stuff that can be written in Python. Yeah? I mean, you're not forced to write the whole thing in C++. You can certainly do this kind of mixed language module where, you know, certain aspects of the wrapping, if they're easier to do in Python, why not do them in Python? I did have that module in here. It was empty, except for, in fact, you know, by the time I finished, it was empty. But you could put Python code in there, for sure, to help you do the wrapping. And then you could, if you did that approach, you could expose APIs that were less Pythonic using pybind11 and then make them fully Pythonic in the Python. Yeah? Yes?
So the way you did the translation from iterators in C++ to Python iterator, if the Python side keeps holding that iterator or not, kind of, I mean, if you do another operation on the C++ side and then the iterator becomes invalid.
Right. Had we had like another 3 hours, we could have talked about all the other arguments that go to PyMakeIterator, which are various policies which control the lifetime of the objects that are being held onto. So there is quite sophisticated control for object ownership in pybind11, because of course you can get into a fight between the Python garbage collector and whatever your C++ wants to do in terms of ownership, and you do need to be careful. And I will confess that this example is carefully constructed to avoid any of those issues. Yes?
Is it possible to debug by stepping from the Python code into the C code and back here?
Yes. Yeah, in GDB it is. My colleague Austin Bingham has written some Gdb plugins that allow you to do exactly that. You can step from one language to the other, back into the other language, back into the other. I'm not smart enough to write plugins like that, which is why I work with Austin. But you know, if you're in like Visual Studio or something without GDB, my guess is not. Okay, are we done? Thank you all very much for your attention.